Hi. Hello. How are you? So, man, intermolecular forces and physical properties. Okay. We're just going to go ahead and get started. Intermolecular forces and physical properties of matter. The physical properties we'll discuss will be freezing points, boiling points, vapor pressure, surface tension. Okay, and I'm going to go directly to my notes screen. Here we are. Let's choose us a color, shall we? Shall we go with the dark? Let's do it. And now let's choose us a pen color, and it should be light, right? Enter. Let's get us some lines so that we can be neat. Intermolecular forces and physical properties. So purely conceptual, not mathematic in nature. Okay? So, remember we've talked about our intermolecular forces. It's the force that holds one molecule to the other. So we will look at physical properties such as boiling points. Sorry, I was thinking. Freezing points. Surface tension. Vapor pressure. These are the physical properties we will be discussing in relation to the strength of a molecule or substances, intermolecular forces. We may not see something called capillary action. Okay. And let's leave it at that for now. Now, if a substance has strong IMFs, we will discuss their boiling points, and if a substance or physical properties in relation to a substance that has weak IMFs. So this will organize what we learn and discuss. All right? It will help us to organize our answers or our information. We're going to make a chart. And maybe let's go like this, right? Let's go like this. Let's go like this. Let's go like this. And let's delete this and go like this. Okay? And we'll go like this. Now let's talk about boiling points, right? Boiling points. What happens when we boil? Well, you know that we've got a liquid that has some attractive forces, right? They are there. They're not as strong as they would be in a solid. And we know that if we add heat, right, to that liquid, then what's going to happen? The intermolecular forces are going to be overcome, and we're going to have a gas. Okay? All right. Well, let's think about it. In order to boil this, the energy must overcome these forces of attraction, right? To boil, all forces of attraction must be overcome, right? So that one molecule can break apart from all the other molecules and become a gas, and they can all become gases, and they're no more They're no longer stuck together as a liquid. They all must be overcome. Well, if the forces are strong, will it be easier or harder to overcome them? Then more energy is required to overcome them, right? And we see that is evident by high boiling points, right? We've got to get this liquid to a higher temperature in order to overcome those intermolecular forces. So if a substance has strong IMFs, then it also has relatively high boiling points. If a substance has weak IMFs, right? If the forces are weak, then less energy and therefore less heat. Required to overcome them. And that becomes, we see that as we observe low or relatively low boiling points. Okay, so this here would be relatively low. Okay, now freezing points. Think about what has to happen to freeze. We've got to have the molecules that are in slight random motion in the liquid form, right? We've got to remove the heat, right? We've got to take the heat away so that it can solidify, okay? All right. If the particles are have strong attractions, let's say that, if the particles have strong, we should write this over here so that we keep our notes kind of synonymous, because we talk about strong on this side. If the particles have strong attractive forces, then it's easy to bring them together. All right? And we see that we don't have to remove as much heat. Therefore, we do not have to get it as cold, and we actually see higher freezing points. Some students get confused there, right? Not as much heat needs to be removed. We don't have to get it colder and colder and colder for those particles to begin to form their intermolecular forces, to form in that solid structure for them to overtake over, right? However, if the forces of attraction, if the attractive forces are weak, right, then those particles do not want to come together. And more heat must be removed to force them together. To form that solid. And what we see is we see lower freezing points. We have to get them colder and colder and colder. That would be like nitrogen, right? Think of nitrogen as a very non-polar compound, very non-polar, very small. And what we see is it's got very weak London dispersion forces, right? Weak LDFs, London dispersion forces. So in order to turn gaseous nitrogen into liquid nitrogen, you've literally got to get this, right? This is actually, yeah, well, this is actually the opposite of boiling. This is the condensation point. So you've got to get it really cold, like negative 300-ish degrees Celsius, right? But you got to get it really cold to push those together. That would be a condensation point, right? This is a condensation point. But you see how we've got to remove so much heat to make that happen. Okay, if we were to talk, so a freezing point, strong IMFs is low. No, it's high, right? You don't have to get it as cold. Weak IMFs is low. You must get it very cold. Surface tension, if the IMFs are strong, is high, and here is low. Let's look at a picture of that. I've got one right here. Where did that surface tension picture go? I think I can find it here. Here's your solid, right? Here's your solid with your very organized, strong IMFs to the gas with no IMFs. I was pretty sure that I imported this and could draw on it. Sorry, there's a picture here of surface tension. There, right? And surface tension, these interior molecules, see how they're attracted to everyone? Well, oh, I got to do viscosity too. So it helps to hold things. Surface tension allows this paper clip to sit there. Surface tension is ability to, I'm sorry, I just really lost track of myself, but let me get back on and finish this up for you guys. I apologize. That was not smooth. That was not smooth. Surface tension, guys, and pretty good definition, is a resistance to increase surface area. So a resistance to spread out. So, and you could see that that would be high if particles were attracted to each other, right? So the higher the attraction, the higher that surface tension. That's why bugs can walk on water, right? Water has very high surface tension. Bugs can walk on it. Vapor pressure, and what was the one I just saw there? Oh, viscosity. I'm going to add viscosity here. All right. Now, when we talk about vapor pressure, I'm going to write PVAP. Okay, PVAP is vapor pressure. It is caused by the evaporation of a liquid in a closed container. All right, and you'll think about it. Here's our container. Here's our liquid. Here's our container. Here's our liquid. Here we have strong IMFs. And here we have weak IMFs. Okay? Which one of these is going to evaporate more readily? The one that is strongly attracted to itself, or the one that is weakly attracted to itself? The one that is weakly attracted to itself. So we'll see much more evaporation here, many, many more gas particles, right, have evaporated due to the weak attractions. All right, and over here, we would only see a few particles of vapor. So here we've got lots of vapor, which is just a gas particle, right? And therefore, we have a high vapor pressure, right? That vapor that is up there is pushing against the walls of the container and causing a force, a pressure to be applied, okay? Over here, we have small amount of vapor, small amount of vapor, and therefore we have a low vapor pressure, low P vap. Okay? So if we have strong IMFs, we have a low vapor pressure. If we have weak IMFs, we have a high vapor pressure. Capillary action, high, low, there's more to talk about there. Viscosity, high, low, and I do need to add one more. Viscosity is a resistance to flow. And all right, I'm not going to get too much into that. And volatility, last word, is the ease with which a substance evaporates, a liquid evaporates, right? So if you have high, or let's say strong IMFs, right? This time we don't have a closed system, right? Well, if we have strong IMFs, what does that say about us? Just a liquid sitting there. Is it going to evaporate quickly? No, it's going to be less volatile, right? Less will evaporate. And if we have weak IMFs, where these particles do not have strong attractions, it's going to be more volatile, such that we will have many more gas particles exiting the liquid phase and entering the gaseous phase and going into the atmosphere. Okay. I did skip over capillary action. And let's add volatility to our chart up here. I apologize, volatility. And it would be low and high. Okay. Capillary action, to expand upon that just a little bit, involves two processes. One is adhesion and one is cohesion. This is an attraction for another substance. And this one is an attraction for oneself. Right? We see this, move that, when would we see this? This is how, if you have a plant, right? We've got these tall plants, and right, with these trees, and the water actually has to get up here, right? Water has to flow against the force of gravity and get up the tree, and it moves this way through capillary action. It also explains when we look at a cup of water or a small cylinder of water, we see the shape of the meniscus do such. All right. So whenever, I'm going to redraw that. Whenever you're looking at a graduated cylinder, you should have been taught that when water is in there, the meniscus does this, right? The meniscus for water is concave, right? That is because the adhesive are stronger than the cohesive. Okay, the adhesive is water with the sides of the container, and the cohesive is water with itself. In opposition to that, if I had another graduated cylinder, and in this graduated cylinder, I put mercury, I would have the opposite shaped meniscus. The meniscus for mercury, liquid metal, is convex. This is because the cohesive is stronger than the adhesive. Okay? Good job. We'll talk about it a little bit more, but I think that's good enough for now. Okay?